for example. So this is a damped harmonic oscillator with a periodic external force. So let's find this. The theory says if you want to solve a non-homogeneous, non-homogeneous means you have a non-zero external force. The general solution is equal, that's written down here, is equal to the homogeneous plus one solution of it. So what we're going to try and do here is, first of all, write down the associated homogeneous system. So it would be r double dashed of theta plus 2r dashed of theta plus r of theta equal to 0. So you solve it first equal to 0. We know how to solve this. We write down the auxiliary equation. Now let's look at it was 1, 2, 1 is the coefficients, and we'll use lambdas. So 1, 2, 1. So I recommend factorizing this. So to do the factorization, I'm recommending the AC method. So it's 1 by 1 giving you 1, and there's only one possible factor, is 1 and 1. Can it make 2? Yes, that's good. So we've lambda squared, and I can rewrite the 2 lambda as 1 lambda plus 1 lambda. Plus 1 is equal to 0. Okay, now I can take out the common factor of lambda out of the first two, and I'm left with lambda plus 1. And I need to take something out of the second two that leaves lambda plus 1 again, and the only reasonable answer there is 1. Now what happens is I've got a common factor here of lambda plus 1. So I can take that out as a common factor. And what am I left with? Lambda plus 1. Now two numbers multiplied together, lambda plus 1 and lambda plus 1, give you 0 exactly when one of them is 0. So either lambda plus 1 is equal to 0 or lambda plus 1 is equal to 0. And of course they're the same equation. So we end up with, if we take away 1 away from both sides, lambda is equal to minus 1. So we have a repeated root. So the repeated root says, okay, now here just be careful, we're not dealing with t, we're dealing with theta. So I'll just be aware of that. So we've got e to the minus 1 theta, and we're tempted to, okay, so we multiply that by a, and we're tempted to do b multiplied by e to the minus 1 theta. But as we explained in a previous lecture, they're not two different solutions. So you change this one by multiplying by t. Now t, of course, would be wrong because it's not t here, it's theta. The role of t is played by theta. And so this now is the homogeneous solution, or h of theta. Okay, so now the problem is finding a particular solution. So let's just go back and write down the differential equation up the top. So it's equal to sine 2 theta. Now this thing on the left hand side, excuse me, the right hand side, is a wave with a certain amplitude 1 and a certain frequency. And what we're going to do is we're going to pick a wave. We're not going to agree with the amplitude necessarily. We're not going to agree with the where it starts. So this starts actually, if I did it properly, failing badly here, sorry. Trying to something, it's kind of hard to draw the way because it's not a very good wave. See the way it started at 0, sine starts at 0 and increases. We're not going to say that it does the same as that. The only thing we're going to agree on is that it has the same frequency. So maybe it starts a little bit later, for example, or maybe it starts something like this. So that would be similar frequency. It could actually be of a higher amplitude, something like that. But the only thing we're going to agree on is that it's a 2. So the amplitude is the number that multiplies here. We're not going to say anything about that. And if it's to start not necessarily at 0, you need a sine and a cos. But the thing we're definitely going to have is the 2. So we try this trial solution. Definitely have the 2. We need a sine and a cos to capture it starting at not necessarily 0. And we multiply by c and d because we're not saying anything about the amplitude. So the question is, can we force this trial solution here into solving this blue equation up the top? So what we're going to do is we're going to find the 2 derivatives. Now maybe we'll slow down here and find the derivatives. Maybe you've space somewhere like here. So we're working now. So we got the trial solution is c. I haven't really left any space. Sine 2 theta. So we're going to the next line plus d cos 2 theta. Now, if you did c cos 2 theta and d sine 2 theta, that doesn't really matter. So let's do the first derivative here. So fix the constant c. Then the chain rule says if you're differentiating sine of 2t, you differentiate the outside function, that's cos, evaluate at the inside, which is 2 theta, times the derivative of 2 theta, which is 2. Plus, fix the constant d, and then differentiate cos of 2 theta. The derivative of cos, the outside function, cos of x, is minus sine of x. Evaluate at the inside, which is 2 theta, and then multiply by the derivative of what's inside, which is 2, and then use this bracket to tidy it up. And then finally, the second derivative of the trial solution. So fix the constant 2c. The derivative of cos 2 theta, similarly, is going to be minus sine 2 theta times 2. Plus, and the second one, fix the constant minus 2d. And the derivative of sine of 2 theta, similarly, is cos of 2 theta times 2. So that's where these things come from. So we have 2c cos 2 theta and minus 2d sine 2 theta. And then the next one, they're both negative, and it's 2c by 2 gives you the 4c, and the 2t by 2 gives you the 4t. So now we're going to force all of these yolks into the equation up the top. So all the stuff that's calculated in this, all this data is going to try and be forced into that, and see can we find values of c and d that make it work. Okay, so let's go. So let's do the second derivative of the trial solution plus twice the derivative of the trial solution plus the trial solution. And we're trying to get sine 2 theta. So let's see what we can do. This is equal to, the second derivative is written here. It's minus 4c sine 2 theta minus 4d cos 2 theta plus twice and the derivative, which is 2c times cos 2 theta minus 2d times sine 2 theta, that's in the previous paragraph, plus the trial solution, which is c, where's the trial solution? Oh, it's in purple, c sine 2 theta plus d cos 2 theta. And now let's put all the sines and cosines together. So this is equal to sine of 2 theta. So I'm going to highlight all the sine terms. So you're going to have this one, but don't forget the 2, and this one. So the first one gives you minus 4c. That one isn't too bad. Well, we'll be a bit careful, right? We'll be a little bit smart. So look at of these 3 sine terms, the first one and the third one add together. Minus 4c plus c is minus 3c. And then look at the other one. We got the minus 2d, but that's actually multiplied by 2, so it's minus 4d. Now let's look at cos 2 theta. Okay, so the cos are all the other terms. We'll add the first cos and the last cos. That's minus 4d plus d is minus 3d. And then the other one is 2 by 2c, which is 4c. And what do we want this to equal to? Well, we wanted to solve the light blue equation up the top. We want this to solve, I put an exclamation mark because I kind of want to force it, equal to sine of 2 theta. Now you compare coefficients. What is the coefficient of sine? Well, there's only one sine on the right, so I want this to equal 1. And then the question becomes, how many cos's on the right? Well, there's 0. So I want this to be 0. If I can find values of c and d that make the first thing 1 and the second thing 0, then I have a good trial solution. So off we go. Now they're just, obviously you're experts now in linear equations, but these are just simple differential equations, so we'll keep it simple. Minus 3c minus 4d to be equal to 1, and plus 4c minus 3d equal to 0. You can solve these however you want. Maybe we'll multiply the first one by 4 and the second one by 3 for argument's sake. So if we do that, we'll get minus 12c plus 16d minus 16d equals to 4. And the other one, you get 12c minus 9d equal to 0. And we're going to add these together. And we get minus 25d is equal to 4. And we're going to divide both sides by 25. D is equal, by minus 25, minus 4 over 25. Now we're going to sub this into the first one. So therefore we have minus 3c minus 4 times d, which is minus 4 over 25. This is it's tricky enough. And then minus 3c. Now I've got a plus 16 over 25. I'm going to actually take that away from both sides. And if I do that on a calculator, I'm fairly sure I end up with 9 over 25 over here. Okay. And then I divide both sides by minus 3. I end up with c is equal to minus 3 over 25. Now I'd like to check my answer, but I don't think there's... okay, what I'm going to do to check my answer is I'm just going to sub these in very briefly into the equation. So the first one, 4c, would be like minus 12 25ths, minus 12, minus plus, yeah, so it works on the second one. And the first one, I'm kind of seeing 9 25ths, plus 16 25ths, yeah, they work. Okay, so we have now our, what's called a particular solution. If the c is minus 3/5, so it's c is by sine 2 theta. So minus 3 over 25 sine 2 theta plus d, which is minus 4 over 25 cos 2 theta, is a particular solution. So if we add this particular solution to the homogeneous, we'll probably have to go to the previous page to see the homogeneous. No, it's up the top here. Where is it? Oh yeah, it's the thing here in, oh god damn it. Thank God. So here's the homogeneous. So add that to the particular and we're done. So it's 2 minus 1s. So that's the homogeneous plus the particular, and that is the general solution. Now what we'll discuss at the start of next week is what happens if basically our chancing our arm doesn't work, and we'll discuss different ways that can happen and how to get around it. And then what we're going to do is we're going to say, okay, well, what's the solution if I actually know the initial displacement and the initial velocity? In other words, how do I find this A and B? So that's what we'll do next week.